Hello everyone, my name is Brandon Morgan, and in this video I'm going to be going over the implementation code I gave on my Medium article. So my Medium article is called Unit 3 Genetic Algorithms Part 1, and this is simply not freely available. It is available on the Medium website where I go into depth and in continuation of my series on evolutionary computation. So if this is your first time seeing this video and you don't know exactly what I'm talking about, please check out my article, as it'll basically give a good overview of genetic algorithms and evolutionary computation. So at the very end of the article, I gave a short trivial example problem along with some code in Jupyter. However, the code was kind of long and kind of complex, so I've decided to make a video and explain the topics. So what exactly was the problem statement? Simply, the problem statement was the following. We are given a simple function, negative x squared plus 3, and we want to maximize it, meaning we want to find the maximum. Well, we know from calculus that we can calculate the derivative and whatnot and see the critical points where it equals 0, blah, blah, blah. But visually, we can definitely see that the max occurs at 0 when f of 0 equals 3. So now we have some design issues for our algorithm. First off, what will our initial population be? Well, it'll simply just be a uniform sampling from the domain, from negative 3 to 3. And to keep things small and simple, it'll have just an initial size of 5. What will our fitness function be? Well, it'll simply just be the original function itself, because that's what we want to maximize. How will we encode our chromosome? Our genome? Well, we are going to be using floating point representation. How will we select which individuals to mate and reproduce? We will use a combination of roulette wheel and elitism. Now, if you're unfamiliar with these topics, please check out my article, as I gave a very good overview of them in detail. For reproduction operators, we're going to be using namely crossover and mutation, where crossover will simply be it'll be the average of the two parent functions, where we'll implement a gamma. And I'll go over this in detail when we actually look at the Jupyter code. And for mutation, it'll simply be some type of random uniform value that we'll add to our offspring. Now, as stated before, we don't always want to mutate or crossover, because if we do, we might actually lose the genetic information from our parents. So we're only going to mutate and crossover probabilistically. And so we're simply going to mutate or crossover only about 75% of the time. And lastly, our stopping condition is when we have reached our maximum generations. All right, this should be a good overview of the design of the algorithm. And now I'm going to head over to Jupyter and we're going to implement this. All right, now I'm back at the Jupyter notebook. This is the notebook I gave in my Medium article, and you can click on it and you can find it on my GitHub. So first, I'm just going to explain it. So first, we're going to define our fitness function. As we can see here, it's simply going to be our function itself. We're going to then initialize our population size. We're going to declare our domain from negative 3 to 3 with a lower and an upper bound. And then we're going to create our initial generation by simply creating a uniform random sample between our lower bound and our upper bound. So these are our initial generation individuals. So as we can see here, remember the minimum occurs at negative 3. So we can definitely see that this one is extremely close. If we calculate the fitness of our function, then here are our fitness values. The minimum is not at negative 3, it's at 0. The function value is at 3. That's what it is. So we can calculate the fitness values of our individuals as so. Now the problem is that we're using roulette wheel selection, and how that works is we divide each fitness value by the sum of the fitness values for that generation. Well, the problem is if we were to sum all these up because they're negative values, it would not make sense. So how do we get around this problem? Well, we can get around this by scaling our fitness values. We can scale them by simply adding the absolute value of the minimum of our fitness. So the minimum value is at negative 5.8. So what we do is we take the absolute value of our minimum and then add that to each of our fitness values. So we did this here, and we can see here that the new scaled fitness is as shown, where the minimum is now at 0. So now we can actually sum these up and it would make sense. So here below we sum them up, and then we divide the scaled fitness by the sum to create a proportion. So now we can say that this individual has a 0% chance of being chosen for selection, while this one has a 26% chance, this one a 37, this one an 11, and this one a 24. Now remember, the proportion or the chance of an individual being selected for mating is proportional to their fitness value. So the higher the fitness value, the better chance it has of being selected. So now what we need to do is let me back up a little bit. So now since we have a proportional selection, we now need to choose our elitism. So for elitism, we're going to choose the best 20% of our population to continue on to the next generation. So how do we do that? Well, the first thing we're going to do is we're going to create a range of indices. So we're going to simply sort this distribution, and then we're going to take the best 20%. But the problem is, if you were to sort the fitness values, you won't retain their original indices. So we have to create another set of indices that we append. And hopefully you can see what I mean by that in a second. So we create a set of indices, then we column stack, which simply means we take our distribution, we stack it, and then we stack these indices as the second column. So then we have our temporary array. And then what we do is we sort on that temporary array based on the fitness values, which is the 0 column. So we sort based on all the rows on the first column, and then the argsort returns the indices of the sorted order, and we use those indices to extract the temp, or the original values. So now we have our sorted temp matrix. So now we have our sorted fitness values on the left-hand side, and then now we have our sorted indices values on the right-hand side. So these indices represent the original index values of our fitness values. This will be extremely beneficial in the future. So now we have done that. We've sorted our fitness. Now we need to extract that. So we do that as so. We take those sorted values and store it into distribution. And here we printed it out just so you can see exactly what it is. It's simply just the first column. So now that our fitness values are sorted, we can now take the best 20%. So how do we do this? Well, the best 20%, remember 20% of 5 is 1. So simply we're just taking the best individual. Well, the best individual occurs at this index, which is 5. But let's say our elitism was 40%. 40% of 5 is 2. So the best 2 would be these 2. And then 60% would be these 3, and then 80% would be these 4. So now how do we get these values? What we do here is we calculate the best index. So simply that is the size minus the int of the size times elitism. So let's say in our example, elitism is 20%. So size times elitism, which is 20% of 5, is 1. So we have size minus 1, which is 4. Best index. So best index starts at 4. As we can see, 0, 1, 2, 3, 4. So it starts at 4. And simply what we do is we take a range from the best index, starting at the best index, to our size. So since our size is 5 and our best index is 4, it would be a range of values from 4 to 5. And then what we do is we extract these original indices from our temp matrix. So we plug in our best index into our temp to get the original indices. Now, what if our elitism was 40%? So if it was 40%, our best index would instead be 3. So now what we do is take a range of values from 3 to 5. So we would extract these two values. But the problem is, what we want are these indices values. So we take these best indices, and we get those rows, which would be these two, and then we get the first column, or second column, and that would return us 1 and 2. And then these would be the best indices of our original individuals in non-sorted order. So hopefully you can see why we are using indices, so that we can extract the original individuals. So now that we have our best indices, it's time to move on to our selection process. So now we're going to create a cumulative distribution. We simply call this function here, which creates a cumulative sum of our distribution. Now, what exactly does that do? Well, here we have our distribution right here. Simply, it takes each value and it adds it to the previous sum. So this would be 0. This would be 0.11. All right, I'm back. I had to make a short stop. But as I was saying before, simply how it works is the following. It takes its current value and adds it to the sum of the previous. So this would be 0. This would be 0.11. And this value would be 0.24 plus 0.116 plus 0 as we can see here. And then this 0.26 would be its value plus this, plus this, plus this, as we can see. And because we created a distribution of values, its sum will equal 1, as we can see here. So now we're going to use it for our roulette wheel selection. So how are we going to do that? What we do here is we create a sample of values, usually of the size of 5 in our case, because we have 5 individuals. So as we can see here, we create 5 random values. And wherever these values lie in these ranges is the index of the chosen selected individual. So for example, 0.5 lies in this region here, so it was selected to be the third index. So 0.355 was here, so it would be the second index. Second index, this appears to be the first index, and this would be the fourth index. So kind of spoiled the next section, but simply what we do here is we have an array of our selected indices. We loop over each probability in our random value, and we set an index to 0 each time. That way we reset it. So we're going to say while our random value is bigger than the cumulative sum at this index, we increase the index until it is bigger. So for example, we start at 0, which would be here. So 0.5 is bigger than 0, so we increase our index to here. 0.5 is bigger than this, we increase. Oh no, 0.5 is not bigger than 0.6, therefore we have our final index. So these are our selected indices: 3, 2, 2, 1, and 4. So now what we need to do is we've just now calculated our first set of parents. We need to calculate our second set of parents. So we do that by simply randomly choosing from our selected indices without replacement. So now we randomly select our mates, and now we have our indices for our parents, the first set and the second set. So now let's actually retrieve those values back from our original indices. Excuse me, not original indices, original generation. So what we need to do first is the following. These are the indices from our temp function, temp matrix. So what we need to do is get these indices. These are the indices that actually matter. So we do that by using these to index our temp and then extract this column. This will get us the original indices from our original generation. So what we do is we have our selected indices as defined above. Then we index our temp matrix, get the first column that will return us our original indices for our individuals. Then we convert that to an MP array of type integer, simply because it's going to interpret it as a float, and you can't use floats to index. You need an integer. And then we're going to convert this to a list, simply because if you don't convert it to a list, it won't properly index correctly. So now that we have our original indices, we can now index our initial generation to get our individuals. So now selected, this array is the actual values of our individuals from our initial generation. And then we do the same thing for fitness. So we index our fitness array, previously defined, to get the fitness values for our selected. And then we do the same thing for the second set of parents, as we can see here. And then we print out the values. So here are our selected individuals. So this is the first set of parents. These are their fitness values. And then this is the second set of parents, and these are their fitness values. So now that we have done our selection, it's time to perform reproduction by creating the offspring. So first things first is we're going to perform crossover. We're going to perform crossover probabilistically. So 75% of the time, we're going to create an offspring through crossover. The other 25% time, we're simply going to choose the fittest parent from as the offspring. So we're going to create a range of random values. And if that random value at the index in our for loop is less than our P of cross, then we perform a crossover technique, which in this case is an average. Now, if you remember from the post, the average is simply the following formula. It's 1 minus gamma times your first parent plus gamma times your second parent, where gamma can be any value between 0 and 1. Now, what we can do here, we can usually randomly sample uniformly or normally, but in this example, we're going to do it uniformly. So we're going to sample our gamma from 0 to 1, and let's say, for example, if our gamma value was 1, then this right here would be 1 minus 1, which is 0, meaning that it would not take any gene information from the first parent, but only take gene information from the second. Therefore, gamma values near 1 favor the second parent, whereas gamma values near 0 favor the second parent. So that way, when we sample uniformly random, you get a range of values between both of the parents. So we just calculate our gamma value, and then we plug it in here, and then we get our child, which is an average, some type of linear combination of our parents. Now, as stated before, if we don't cross over, we choose the fittest parent as our offspring. Then what we do is we append the child to an offspring list, as we can see here. And these now are our offspring. So let's see if any of these were not crossed over. So negative 1.6, 1.7, 1.79, 2.48. So here we have, this is the only value that was not crossed over, as we can see. So the other 4 were actually crossed over. So now that we've performed crossover, it's time to mutate. This is how we introduce new genetic information. So the question is, how much should we mutate by? Well, usually it's about 1% of the entire domain bound. So we take the absolute value of our lower bound plus the absolute value of our upper bound, add them together, and then times it by 1%. So our lower bound was -3, our upper bound was 3, so this value should be 6. And then we say 1% of 6, which is 0.06. So 0.06 is the maximum value we are going to mutate by. And we're also going to mutate probabilistically. Now, instead of like in crossover, where if you don't crossover, we choose the fittest parent, and mutation, simply you just don't mutate. You leave it as is. So we calculate our random values. If it's less than, then we mutate the offspring by adding some random uniform value between our negative bound mute and our positive bound mute, which would simply be negative 0.06 and 0.06. So here we have our offspring. We can see how much they've mutated by. So this value mutated by approximately 0.05. This one mutated by 0.03. This one by some value. And this one did not mutate whatsoever. So the same value that did not cross over is actually the same value that did not mutate. So now that we've created our offspring, it's time to check out how well it does. So we're going to first see our new fitness value. So we calculate the fitness of our offspring, and we're going to calculate the indices again. And we're going to do this simply because when we performed elitism, we want to replace the worst 20% of our new offspring by the best 20% of our previous generation. That way we can always keep the best over to the next generation, just in case they weren't chosen. Now, one thing you might notice is in this temporary argsort, NP argsort, I take the negative value. This is because I want the largest value up top and I want the worst value at the bottom. So as we can see here, this value here, this index is the third, so 0, 1, 0, 1, 2, 3. So this individual had an extremely terrible fitness value. So we want to replace this with the best of the previous generation. So as we did before, we column stacked the new fitness with the indices, then we sorted them, and then now here we have our sorted individuals. So now it's time for elitism. We want to replace the worst 20% with the previous generation's best 20%. So how do we do that? Well, if you remember correctly, we created our best index all the way up here, best index, and we use best index to create our best indices. Now it seems I did not use best indices, but you could use it as well. And I use best index until size, which is exactly the same as best indices. I don't know why I didn't change this, but simply it's the same thing. You take your best index and you take a range of values from that to your size, and that will get you the worst 20% or worst whatever percentage of your elitism would be. So now we take our worst, which would be our best index in our case is 4. So we sample from 4 to 5, which would only be 4. So our fourth row would be here. We get its sorted index, which would be 3. So now we have our indices to replace. We convert this to an array of type integer, convert that to a list. So as we can see here, 3 is our index to replace, because this individual is terrible. So we create our next generation by copying the offspring. Then we say add the indices to replace. We are going to get the original values, our best indices. Okay, there they are. That's where I used them. Our best indices from our initial generation. So now we have our new generation. So now what we do is we see the fitness values of our next generation. So we calculate the new fitness values, we calculate the mean and the best. Now we can definitely see here that the best previously from our old generation was 2.7. The best of our new is now 2.995. So we've increased by about 2.7, and then our mean also increased drastically from negative 1.25 to 2.29. So we are definitely heading into the right direction. So this would actually be one iteration of our total algorithm. We simply need to repeat this process over and over again until it converges. So I've taken the liberty of creating this function here, which simply does that process for us. It simply does everything I've just now talked about. It holds all the components. We take our initial generation, we store it into a variable called gen, calculate the size, find the max value to mutate by, its fitness. We scale the fitness, simply because we don't want any negative fitness values. We create our distribution. We then take that distribution and pair it up with column stack of the indices. We sort those values so that we have that way we have the indices sorted with the distribution itself. Then we find the best values for elitism. We create a cumulative sum for our roulette wheel. Here we have our selection for our first set of parents, and then now we have our second set of parents by randomly choosing from our selected indices. Then now we take those indices and we put them back into our temp matrix, and then get the original unsorted indices, and then put that back into our generation, as we can see here. This will give us our original values. Then we create our offspring through crossover first, and then we do the same thing for mutation, and then we replace the worst of our next generation with the best of our previous. And then we set up our next generation for the next iteration by replacing those values. And then if you were to call this function, as you can see here, as we can see, we simply take our size of our initial generation, our bounds, we create our initial generation, and then we create our bounds again, and then we plug it into our function, and then here we have the output. So we start at a mean of negative 1.7 with a best of 2, and then only after 10 generations we've already reached the max, roughly at 3. And if you're curious, if you want to see what the actual last generation looks like, I printed it out here. Now these values are tending towards 0, however they're not exactly 0. So if we were to continue this process, a lot of times it would eventually converge. So hopefully this video has answered any questions you have about the code. Hopefully I've walked through it all. Hopefully you can understand it. As with all things, there are different ways to code, so hopefully this is a nice and intuitive way to understand. And stay tuned for the next post where I will go over another example of a genetic algorithm, except we'll go over a more advanced problem, specifically a benchmarking test function. So thank you.